video, we're going to look at two probability distributions. In the first one, a numbered ball is drawn at random from a jar containing 10 such balls, and the number on the ball is observed. So, in this case, the jar contains 5 balls that are numbered 1, 1 ball that's numbered 2, 3 that are numbered 3, and 1 that is numbered 4. And we're asked to do a distribution for the outcomes from 1 to 5. So 5 out of 10 are numbered 1, so the probability that the ball that is drawn is numbered 1 is 0.5. 1 out of 10 is numbered 2, so the probability to draw a single ball that is numbered 2 is 0.1. 3 balls are numbered 10, so the probability of drawing a ball numbered 3 would be 0.3, or 0.3. For 4, there's only 1 ball numbered 4, so the probability there would be 0.1 or 1/10. And there are no balls numbered 5, so that probability is 0. Notice that the sum adds up to 1, and so all different outcomes have been considered, as well as one additional one. So now when we draw the probability histogram, the numbers from 1 to 5 go on the horizontal axis, and we think about them having width, each number having width 1. So for 1, we use the width from 0.5 to 1.5, for 2 from 1.5 to 2.5, etc. On the vertical axis, we're going to want to list 1/10, 3/10, and 5/10. So let's try to draw 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Divisions there. And 5/10, 1, 2, 3, 4, 5 is right here. So we draw a horizontal line from 5 and down. That's counting 5/10. This is the probability in tenths. Add 1/10 for the 2. 3/10 for the 3. 1/10 for the 4. And no height for the 5. So this would be the probability histogram with outcomes on the horizontal axis. Discrete outcomes here. This is different from what we've done in other places in the course. In the second example, we're given a binomial experiment with a probability of success P that is performed n times, where n is 4 and P is 0.05. And so we are wanting here to, let me just see if I can get rid of a couple of these dots here. We're wanting to find the probability of each of the outcomes. Since the experiment is conducted 4 times, we could have 0, 1, 2, 3, or 4 successes. And those successes are what is called R. And so for the probability for 0 successes is the combination of 4 things where 0 is selected, where 0 of them are selected, times 0.5 to the 0 times the probability of none success, which will also be 0.5 to the 4. So this is going to be 1/2 to the 4th, or 1/16. And 1/16 as a decimal is 0.0625. In the second case, it will be the number of combinations where we have n trials and 1 success is chosen. So 0.5 to the 1 times 0.5 to the 3. And so this is going to equal 4/16, or 4 times 0.5 to the 4th. 4/16 is 1/4, or 0.25. For 2, it's the number of combinations of 4 things where 2 are selected, times 0.5 to the 2 times 0.5 to the 2 again. And this time, C for 2 is 4 factorial over 2 factorial, 2 factorial, times 0.5 to the 4th. So this is 4 times 3 over 2 times 1, or 6 times 1/16. 6/16 is the same as 3/8, and that is 0.375. Now, the probability for the 3 here is going to be combination of 4 things where 3 are selected, times 0.5 to the 3 times 0.5 to the 1. This is going to give us again 4 times 0.5 to the 4th, which is 0.25. And lastly, number of combinations of 4 things where 4 are selected, times 0.5 to the 4th times 0.5 to the 0 is going to give us 1 times 0.5 to the 4th, 1/16, or 0.0625. And I want to check that when we add these together, we get 1. And that, in fact, should happen. So let's come back here and go 0.0625 plus 0.25 plus 0.375 plus 0.25 plus 0.0625, and we get 1. And now we're to draw the histogram, and I want to remember that in fraction form these are 1/16, 4/16, this was 6/16, 4/16, and 1/16. So our probability distribution this time has the outcomes from 0 to 4, and here we'll do the probability in terms of sixteenths, and we have to go up to 6/16. So 1, 2, 3, 4, 5, 6, and we'll continue there. But this is going to be 6/16, 4/16, and 1/16. So we start out at 1/16 for 0, probability. For 1, it's 4/16 or 1/4. For 2, it's 6/16 or 3/8. For 3, it comes back to 4/16 or 1/4. And for 4, it comes down. And this is a typical shape for what is called a binomial distribution.